Alrighty now here, partner. We're going to talk about some exponential functions, and our learning target for today is to evaluate and graph exponential functions. But anyway, look at that picture down at the right. That is a molded loaf of bread, and that mold grew exponentially. And that's what we're going to talk about today, how things grow exponentially and how you can figure it out using an exponential growth or decay equation or function. All right, I'm not going to talk that way the rest of the time, but in all reality, mold does grow exponentially, and you'll see kind of a little bit about how that would work in today's lesson, which is about exponential functions. So vocabulary, we just got one term, and it's an exponential function. um, A function that repeated an exponential function is a function that repeatedly multiplies an initial amount by the same positive number over and over and over again. So I guess in this lesson we're not going to specifically talk about how exponential growth, like in a moldy loaf of bread, but that'll be the next one. But this is getting us into how exponential functions look, how their equation looks, their graph looks. But going on, you can model all exponential functions using this formula: y equals a times b raised to the x power, where a is a non-zero constant, b is greater than 0, and not equal to 1. So this is the general graph of an exponential function. It starts off going really slowly up, just barely, tinily going up, and then it starts going up, and then it goes up really fast, and really fast, 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 fast. All right? So that's what an exponential function kind of looks like. Now, let's get into the basics of exponential functions. So what we're going to do today is we're going to talk about exponential functions, um, identifying whether a function is exponential or not. We're going to evaluate them a little bit, and we're going to do some graphing of it as well. Okay? So going back here, an exponential function. Here's the form: a times b raised to the x power, and a can't be 0, so it's not non-zero. B has to be greater than 0 and not equal to 1. Okay? So, important, the exponent has to be the variable. So the exponent has to be the variable. That's something that wasn't listed here, but the exponent has to be the variable. All right? So a couple of graphs here. Y equals 2, so the a value technically would be a 1 here because there's nothing there, times 2 to the x power. It looks like this graph right here. Negative 2 to the x power is going to be just the opposite, going down. If you do the reciprocal, it's going to actually start going slower if you go left to right. And the opposite would be for negative 1/2 to the x power. So there's some examples of them. We're going to talk about them a little bit more right now. So, identifying exponential functions. All right. Question is, does a table or rule that's given represent a linear or non-linear function? So we've already talked all about linear functions. Remember, linear functions have a constant slope, so it adds to the same, it goes up, adding 5 every time. That would be the slope. If you look at this, you can tell if it's linear. If you multiply the same number each time, it will be exponential. So instead of adding the same number, this is multiplying the same number. That's what makes it exponential. So these x's are all going up by 1 here. Plus 1, plus 1, plus 1. But the y's are not going up by a constant number. You are actually multiplying by 3. I'm going to use a dot instead. Times 3 times 3. So this right here, this one would be exponential. Okay. Second one, y equals 3x. Well, you can make a table. And if you made a table, a t-chart, with our x's and our y's, we can just do a couple values, 1, 2, 3. if you plug in 1 for x, 3 times 1 is 3. Plug in 2 for x, it'd be 6. 3 for x is 9. So it's going up by plus 3 every time. It is not multiplying, so in that case, it would be linear. And maybe you recognize this is a direct variation problem, which is a linear equation. So what I'd like you to do now is to try a couple on your own. We have a function, or sorry, a table and an equation, and I want you to determine whether they are linear or nonlinear, or sorry, linear or exponential, and be able to explain. All right, pause it for now, do those, and then I will show you the answers in a sec. All right, problem A is linear. If you look at it, it has a constant rate of change. As the x goes up by 1, the y's go up by 2. Now, if you look at B, this would actually be exponential because we have that exponent. The x is the exponent here. And that's actually how an exponential function looks. It's y equals a times b raised to the x power, which is exactly what this would be. And if you made a table or you made a graph, it would clearly be an exponential function. Okay? So that's determining whether it's linear or exponential. Now we're going to evaluate an exponential function. And I have a word problem here for you. It says, suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. So the function f of x equals 30 times 2 raised to the x power gives the population after x weeks. So the beetles are doubling every week, and after x weeks, we can use that formula to figure it out. It says how many beetles will there be after 56 days. So when you evaluate a function, you're just plugging in for the variable. So in this case, we have f of x equals 30 times 2 raised to the x power, and the x is the weeks, and we know that 56 days. So there's a tricky part. Don't just plug in the 56. We need to know how many weeks that is. That would be 8 weeks. So we can plug in 8 for the x. So we'd have 30 times 2 raised to the 8 power, which would be 30. Well, we're going to simplify this. We're going to take a calculator and simplify this. So 2 raised to the 8 power would be 256. And you multiply that by 30, and I got 7,200. Whoops. 7,200. Or sorry, 680. And that would be the beetle population. So that many beetles. So it says there's 30 to start. After 8 weeks, it'll be up to 7,680 beetles. That's how fast exponential functions, exponential things grow. It's just ridiculous after you get going. It goes so fast. All right, and this is a real thing. These beetle populations double that fast, and you're gonna have tons of beetles if you don't touch them for 8 weeks. So what I'd like you to do is to do this problem here. It says an initial population of 20 rabbits triples every half hour, or sorry, half year. The function f of x equals 20 times 3 to raise to the x power gives the population after x half year periods. How many rabbits will there be after 3 years? So why don't you pause it, try it on your own, and then I'll show you how to do it in a second. All right, so I ended up with 14,580 rabbits, and here's how I did it. It says 3 years, but we're dealing with x is half years. So this would be actually 6 half-year periods. Oops, missing either. So when you plug in for the function f of x equals 20 times 3, this is going to be raised to the 6th power, not to the 3. It's raised to the 6th power because it's half years. And then you end up getting that as an answer. So this rabbit population grows fast. All right, last thing I want to do is graphing exponential function. So in order to graph one, we can do it just like we've done it in the past. But we first need to find the y-intercept by replacing the x value with 0. Okay? So if we replace the x value as 0, um, that'll make the variable term just become 1, because anything to raise to the 0 power is 1. Um, so really the y-intercept is just the number that it starts off with, the number in the front, the a value. So I'll put that right here. It's going to be the a value. That's not a 9, that is an a. All right, step 2, graph the y-intercept. Okay, put it on the graph. Step 3, select 2 values on each side of the y-intercept and then substitute them in. So we want to find, well, we want to make sure it's around that y-intercept to the original equation and find the coordinates. Graph your new ordered pairs, and you have your graph. So first example, graph y equals x raised, or 3 raised to the x power. So the y-intercept right away, we're going to figure that out. I'm going to do x is 0. If x is 0, y is going to be 1 because 3 raised to the 0 power is 1. So the y-intercept is 0, 1. 0 over 1 up. So that's where it crosses. Okay? Um, so now the best values after that in step 2 would be to find values on either side. So we're going to do 1 for x. We're going to plug in 1, 2, -1, and -2. All right? So if we do that, well, 3 to the third, 3 to the, so here's 0, 1. 3 to the first power equals 3. So our ordered pair is 1, 3. 3 to the second power is 9. So our ordered pair would be 2 and 9. 3 to the negative first power, remember that would be 1 over 3 to the positive first power. So our ordered pair would be -1 and 1/3. And then finally, oops, 3 to the negative second power would be 1 over 3 squared, which is 9. So 1 over 9. So our ordered pair would be -2 and 1/9. So if we graph that, we have 1, 3, 1, 2, 3, 2, 9, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, we have -1 and 1/3, so maybe right here, and -2 and 1/9, so really close to here. So if we fill this in, it's going to be very exponential, looking like this, going straight up like that. All right, there's our exponential function. Your turn. Why don't you try this one? It's -0.5 or -1/2 times 3 to the x power. So make a table, graph it, and see what you get. So why don't you pause it right now and make sure you do that on your own, and then I'll show you the answer in a second. All right, so there's the t-chart, and there's the graph for this exponential function. It is a exponential decay. It's going downward instead of upward. All right, final problem here to look at. Real world problem. And it says computer mapping software allows you to zoom into an area to view in more detail. So I'm sure you've done that before with like Google Earth or just Google Maps. The function f of x equals 100 times 0.25 raised to the x power. Miles the percent of the original area the map shows after zooming in x times. So to graph the function, there's our function, and we'll find that you start at 100. 0, 100, that would be your y-intercept. If you zoom in one time, it is 25% the original area. 2 times, it would be all the way down to 6.25%. And you can see the change here as you plug it in. So it's a real world situation here, modeled by a function and an exponential function at that. All right. If you were to do the same thing here, you can also zoom out to do a larger area of the map. The function f of x equals 100 times 4 raised to the x. Model is the percent of the original map the map shows after zooming out x times. Graph the function. So remember when you would graph this, and I'm going to let you do this on your own if you'd like, but make yourself a t-chart, find at least 5 values, and make sure the 1 is going to be the y-intercept, and then 2 on the other side. So usually we do 0 for x. You can do 1, 2 as well. It's totally up to you. That's what I would typically do. And try some negatives. And then see what you end up getting for your values, and then you can graph it. All right? And with these real-world problems, make sure you're labeling the axes as you would looking at a graph of it. So for instance, up on the top in this graph, the x would actually be the number of times zoomed in, and the f of x would actually be the percent of the original area. So that's something that's worth labeling that wasn't labeled right here. All right, but that's actually the last thing I'm going to end with. I'm not going to go through that one in detail with you, but I wanted to give you an idea of that these exponential functions are used in real life. In our next lesson, we talk about exponential growth versus decay. We're going to be doing similar things, only we're specifically going to be looking at what's the difference between if it's going up or going down with growth or decay, and a lot of real world problems with growth or decay in the next lesson. All right. So make sure you take a look at this, assess yourself of whether you met it or whether you will still have to do something else or ask questions to meet this learning target. And I hope to see you next time.